Hello, I'm presenting the design of a 3 RPS parallel robot for high tracking accuracy. We're a group of mechatronics engineering students developing our end-of-career project at the Instituto Politécnico Nacional in Mexico City for the Laboratory of Applied Dynamic Systems in our school, UPIITA. The main team is composed by the students Bibo, Pérez, Cruz, Rumbo, and Sanchez. The project is supervised by the Dr. Flores Hernández and Dr. Juárez, with the help of the student Carrillo Bengumea. The Laboratory of Applied Dynamic Systems conducts research with mechatronic projects, mostly related to solar tracking. Concentrator photovoltaics technology requires high-accuracy solar tracking systems, which can be classified into types: open kinematic chain and closed kinematic chain. The closed kinematic chain systems provide high precision, high stiffness, and high load capacity with respect to their weight. Therefore, it is proposed to design a parallel robot with 3 degrees of freedom in a revolute prismatic spherical configuration to obtain high tracking accuracy, with the design purpose of reducing the tracking error and energy consumption. The BDI 2206 methodology was used for designing the solar tracking system. This allows to design complex systems concurrently and with a functional and interdisciplinary approach. Each revolute joint was constructed with 2 bearings and a shaft. The prismatic joint was constructed with an Acme lead screw, a bronze nut, linear bearings, and a stem, to which a bearing and a universal joint are connected, which form the spherical joint. The solar tracking system is conformed by 3 systems: S1, Central Processing System; S2, Orientation System; and S3, Energy System. The Central Processing System is responsible for measuring internal and external parameters and carrying out the decision making, which include control strategies, the astronomical algorithm, data processing, and conditioning. The orientation system performs the function of positioning the solar collector perpendicular to the sun position. Also, must track the solar path along the day. The robot can reach mainly values between 15 to 90 degrees on the elevation axis and 0 to 360 degrees on the azimuth axis. The energy system is composed by a switch mode power supply with 2 outputs, as well as 2 H-bridge drivers, which help to energize and control the rotation of the motors. 2 different control strategies were simulated: a PID controller and a GPI controller. The best control strategy was the PID controller, which had a tracking error of 0.0031 degrees. The designed system requires low torque to move relatively large loads, so a larger scale robot will have a considerable increase in the amount of energy generated by CPV modules compared to the energy consumed. An estimate of the power that could be generated using a 200-watt commercial CPV module was also obtained, resulting in that the tracker consumed less than 0.6% of the generated power, which means that the system is viable in terms of energy consumption. The system provides high tracking accuracy with low energy consumption, in addition with the high stiffness, good distribution of mechanical stress, and high payload weight ratio of a parallel robot. This work was supported by the Secretaría de Investigación of the Instituto Politécnico Nacional. Thank you very much for your attention.